Jai students, so this is our lecture 2 of our complex lecture series and the topic is binary multipliers. So it is from unit 2 as well. So these are the contents: concept of multiplication, and then we will be designing 2 cross 2 multiplier, 4 cross 3 multiplier and 4 cross 4 multiplier. Okay, so let's start with the concept of multiplication. So 1 bit by 1 bit multiplication. 1 bit by 1 bit multiplication or designing a 1 bit by 1 bit multiplier, that means we are provided with two numbers of 1 bit each. Let's suppose these numbers are A and B. So we need to multiply these, and this multiplication is arithmetic multiplication. Although if it is 1 bit by 1 bit multiplication, then in that case logical multiplication or arithmetic multiplication will not make such difference, because in any case to multiply these two numbers A and B, we will be requiring a single AND gate. Okay, so A is a single bit number, B is a single bit number, and if we want to product them, we want to generate the product of these two numbers, then single AND gate can do the purpose. So this is simple 1 bit by 1 bit multiplication. Now if we want to extend this concept to 2 bit by 1 bit multiplication, that means there are two numbers A and B, out of which A is of 2 bits, A1, A0. Let's suppose it is 2 bit number, A1, A0 are the generalized representation of these two bits, and then B is a single bit number. Let's suppose it is denoted by B. So if we want to multiply A1, A0 multiply with B, then the answer would be A0, B0 and A1, B0. Okay, and these two products are individual products, and these do not have any relation with each other. So if you want to design a circuit for this thing, then we need two AND gates. Okay, this will be A1 and this will be A0, and both these inputs A1 and A0 will be multiplied with a single input B. So this will be a multiplication result. Now it is in form of multiplication result, so I will denote it by M0 and M1. So in that case this Y can also be denoted as M, multiplication result. So in this way we can design basic multipliers. Similarly, if you want to design a 3 bit by 1 bit multiplier, 3 bit cross 1 bit multiplier, that means there are two numbers, one number is of 3 bit, let's suppose A2, A1, A0, and then the second number is of a single bit, let's suppose it is B. Then if you want to multiply A and B, then again in that case 3 bit by 1 bit multiplication will be requiring simply 3 AND gates. Okay, A2, if you want to design a 3 bit 3 cross 1 multiplier. Okay, so in that case we will be requiring 3 AND gates. A2, A1, A0, this is a 3 bit number, and this need to be multiplied with a single bit number, let's say it is B, then this will be my multiplication result M2, M1 and M0. So this is a 3 cross 1 multiplier. Similarly, as long as the second operand is of 1 bit only, we will be requiring only AND gates to perform the multiplication, and these are the very simple circuits. But as soon as both numbers are of 2 bits, complexity start to increase. So let's understand the concept of 2 cross 2 multiplier now. Okay, 2 cross 2 multiplier, that means there are two numbers A and B, and this time A is of 2 bits, A1, A0, and B is also of 2 bits, B1 and B0. Okay, so if you want to multiply A1, A0, B1, B0, and if you want to multiply this, then we will be writing A0, B0. Simply the normal multiplication which we have been doing since our childhood, multiplying this position B naught with A naught first, and then B naught with A1, that means A1 B naught, and then we put a cross here, and then B1 into A naught, that means A naught B1, and then B1 into A1, A1 B1. Okay, and then we start adding. So there is no need to add anything. So A naught B naught will be my LSB of my final result, and then A1 B naught plus A naught B1, these two need to be added. The sum part here, the sum part will be denoted here, and the carry part will reach here. Okay, both these are to be arithmetically added. This is not the logical addition. If it would have been logical addition, then A1 B naught and A naught B1 can be simply added using an OR gate, but this is not logical addition. It is arithmetic addition. So to perform arithmetic addition, I will be requiring adder, not an OR gate. Okay. Similarly, here I need to add this carry and A1 B1. Again, I will be requiring another adder. Another adder will be, it will be again producing, this is my sum part, and again another carry can be produced, which will be produced here, which can be simply be part of my multiplication result as another bit M3. So this is how we can multiply 2 bits. So there is nothing new in that, because this is the way we have been multiplying decimal numbers since our childhood. But when a circuit needs to be prepared for this binary multiplier, we have to first identify the requirements. Wherever we are performing these products, A naught into B naught, A1 into B naught, A naught into B1 and A1 into B1, these 4 products will be requiring simply 4 AND gates. But wherever we are requiring this plus sign, wherever we are finding the need to add 2 numbers, we will be requiring adders, and we can see that not more than 2 numbers are to be added. So if the requirement is adding 2 bits and producing sum and carry, there is a circuit known as half adder which can be used for this. So for this particular stage, for this part, a half adder can be required and another half adder can be used for this purpose. Okay, so let's start designing this circuit now. So first, preparing all the products. 4 AND gates are required. This is A1, this is A naught, and these are being multiplied with this is, and similarly here as well, A1 and A naught. This is my first row, in which this one I have multiplied A1 A naught with B naught. So this is my B naught and this is my B1. So all 4 products are generated. Now I can see that this A naught B naught is not going to participate any further in kind of any addition, and this A naught B naught can directly be utilized as last bit of my multiplication result. So this A naught B naught thing, this is my A naught B naught, this can be my final, this can be part of my final answer M naught multiplication LSB. Okay. Now A1 B naught and A naught B1 are to be added. A1 B naught is this one, this is A1 B naught and this is A naught B1. These two are to be added. Now we have already discussed that for adding we will be requiring a half adder. Half adder will be accepting these 2 bits as input and it will be producing the sum, and we have seen that this sum part is M1. So this sum, this becomes M1, and this carry part, this carry which reached here, this carry needs to be added with A1 B1. So A1 B1 is there, this is A1 B1 and this is the carry. That means these two things again need to be added using another half adder. Again there will be sum and there will be carry. So this sum will become the M2. So this sum becomes this M2 and the carry, this becomes M3. So this is a 2 cross 2 multiplier. Okay. Till now things are getting complex, but they are not complex up to that level. But in case the size of the input numbers exceed 2, okay, let's say we are now interested in designing some complex multiplier of size 4 cross 3 multiplier. Okay, so let's design now a 4 cross 3 multiplier. That means there are two numbers A and B. A is of 4 bits, A3, A2, A1, A0, and B is of 3 bits, B2, B1 and B0. Okay, so these are the two numbers. One number is of 4 bits and another number is of 3 bits. So if you want to multiply these numbers, again the initial step is identical, which we have used earlier as well, like this one, like we used to do in our notebooks for normal decimal multiplication. So let's start with that. A3, A2, A1, A0 multiplied with B2, B1 and B0. So A0, B0, first product, A1, B0, then A2, B0, then A3, B0. So this is the first row. Then we put a cross here, preparing the second row, A0, B1, A1, B1, A2, B1, A3, B1. Okay, putting two crosses and preparing the last row, third row, A0, B2, A1, B2, A2, B2, A3, B2. Then we need to add them. So there will be M0, M1, M2, M3, M4, M5, and there might be some carry and answer might go up to M6, that means total of 7 bits. Okay, but this concept seems to be simple, but the implementation of this concept to realize a circuit will not be that simple, because in the previous case here, while designing the 2 cross 2 multiplier, we need to add only two things at a time. So for adding two things at a time, we have a circuit called half adder. At max, if we need to add three things at a time, we have a circuit named full adder. But if we need to add more than 3 binary numbers at a single time, there is no such circuit existing in our subject, in this digital electronics subject, which can add 4 binary numbers and produce sum and carry, because sum is of single bit, carry is of single bit, and when 4 numbers are to be added, the resultant answer might go into 3 bits. So it is not possible to write sum part and carry part. Okay, so we can see here no problem is there in the initial phase. This initial phase there is no problem. At this phase again there is no problem, no issues are there. But when we will be adding these two things to produce sum here and carry here, now you can check in this stage there are 4 things, 4 bits. Carry from previous stage A2 B0, A1 B1 and A0 B2. That means there are 4 things which need to be added. So even a full adder will not be able to perform this, because full adder can at max add 3 inputs at a time. So in that case, in this case, a normal single bit adder, 1 bit, 2 bit, 3 bit, will not surface. That means normal adder and OR gate will definitely not be serving, because it performs logical addition. Half adder can't be used because it adds 2 bits. Full adder can't be used because it adds only 3 bits. Now we will be requiring multi-stage adder. Okay, multi-stage adder that will be capable of adding multiple numbers, and that too will not be adding these things simultaneously. What we can do here is, we can add these two rows first. We can add these two rows first, producing their sum, and this sum can be added to this third row. Sum plus this third row. That means we will be requiring two-stage addition, because we have limitation. What limitation is there? Because I can't add more than 3 numbers at a time. So in any case, these four numbers can't be added. Okay. So if these 4 numbers can't be added, we will be requiring a specialized circuit which we have already covered in our syllabus, that is a 4-bit parallel binary adder. Okay. So we will be requiring a 4-bit parallel binary adder to obtain this sum. That means the sum of first 2 rows will be computed using a 4-bit parallel binary adder, and then the output of that 4-bit parallel binary adder will be actually the sum of the first 2 rows, and then that sum will be added to the third row. Okay. So in that case, we will be requiring another 4-bit parallel binary adder. Okay. So let's first cover the basic of that 4-bit parallel binary adder. So let's start. What is this 4-bit parallel binary adder? So in simple terms, if you want to use a 4-bit parallel binary adder, the 4-bit parallel binary adder will be accepting 2 numbers of 4 bits each. Okay. Let's suppose these numbers are A3, A2, A1. To avoid the confusion, because A and B, we are using them as our inputs to be multiplied. So I am changing that to, let's say these are X3, X2, X1, X0, and this one is Y3, Y2, Y1, Y0. Okay. These 4 bits of X and Y are to be added using a 4-bit parallel binary adder. Okay. So 4-bit parallel binary adder will produce the 4-bit sum, which can be denoted as S3, S2, S1 and S0, and a final carry, which can be denoted here or here. So for the sake of simplicity, let's denote it here only, carry. Okay. So when we are adding 2 4-bit numbers, answer might go into 5 bits. So this 5th bit will be denoted by this carry. So this is a 4-bit parallel binary adder. It accepts 2 numbers of 4-bit each and produces their sum. So now this 4-bit parallel binary adder is going to be used while designing the multiplier circuit. Okay. So let's design now 4x3 multiplier. So we will be requiring the concept of this. We are going to implement this multiplication table and designing a circuit for that. We can see that the first row is multiplication of A3, A2, A1, A0 with B0. So let's prepare the first row. So we will be requiring 4 AND gates. These are A3, A2, A1 and A0. these are going to be multiplied with B naught. Okay, so first row is generating these 4 products. Then this row is going to be added into the second row. So second row is this one. So this is the multiplication of A3, A2, A1, A0 with B1. So let's design another row. A3, A2, A1, A0, and this is going to be multiplied with B1. Again there will be 4 products. Now there is a 4-bit number from this side, okay, and there is a 4-bit number on this side. Now these two are to be added using a 4-bit parallel binary adder, but before going to that, we have to check that this A0 B0, this A0 B0 is not going to participate in addition, because there is no need to add anything to this A0 B0. So this A0 B0 can directly be taken out as part of my multiplication result, because it is not going to be added with anything. So this A0 B0, this is my A0 B0, okay. So this can be directly used as part of my multiplication result M0, okay. So rest of the things, now this number is of 4 bits and this number becomes for 3, is the number of 3 bits. So I can use another bit as ground, okay. So this can be my 4th bit. So this is my 4-bit number and this is another 4-bit number, okay. So they are to be added using a 4-bit parallel. For sake of simplicity, let's write it 4-bit parallel binary adder, okay. So these are going to be added to produce 5-bit. We have already seen that it produces answer in 5 bits. 4 bits are S3, S2, S1, S0, and 5th bit is carry. So these are my S3, S2, S1, S0, and this is my carry C, okay. So this is the output of first 4-bit parallel binary adder. That means it is the sum of first 2 rows, that means this sum, first row and second row. So the sum of these 2 rows is available to me at the output of this 4-bit parallel binary adder in form of this. M0 is already taken out, and again, like the way A0 B1, we can check here, this is already computed A1 B0 using the 4-bit parallel binary adder, and nothing is to be added in this A1 B0 and A0 B1. So that means this S0 will not participate further and can be considered as M1, okay. So now there is a 4-bit number here, which is the sum of the first 2 rows, and we will be adding this to the 3rd row. But before that, we have to generate this 3rd row first, because it has not been generated. 3rd row means generating the products for the 3rd row, which is saying that A3, A2, A1, A0 need to be multiplied with B2. So let's prepare the 3rd row. You will be requiring 4 AND gates, A3, A2, A1, A0, and they need to be multiplied with B2, okay. So this will generate 4 products, that means the 3rd row of our multiplication pattern. So this is a 4-bit number and this is a 4-bit 3rd row, and this part is this thing, sum of row 1 and 2. This is sum of row 1 and 2. So this sum of row 1 and 2 will be added to this 3rd row. using another 4-bit parallel binary adder. Okay. So, we will be using another 4-bit parallel binary adder. Again, it will be producing 5 bits. 4 of them will be sum S3, S2, S1, S0, and this will be my carry of this adder. And this will be the final step because nothing more is left to be added. So, we can denote this as M2, this as M3, this one will be M4, this one will be M6, and this one will be M7. So, this you can, sorry, M6 is the maximum limit, M1, M0, M1, M2, M3, M4, this is M5 and this is M6. Okay. So, this is this M0 to M6 which was required from this pattern has been realized using a circuit which is comprising of 12 AND gates and 2 4-bit parallel binary adders. So, if you are appearing in an exam which is requiring MCQ questions to be prepared. So, a question can be asked how many AND gates and adders are required to design a 4x3 multiplier. So, the answer is 12 AND gates and 2 4-bit parallel binary adders. Similarly, this concept can be extended to 4x4 multipliers. So, 4x4 multiplier, that means there are two numbers A and B. A will be A3, A2, A1, A0, and this will be B3, B2, B1 and B0. Okay. So, again we can check that in that case we will be requiring row 1, row 2, row 3, row 4. You can obtain these rows. Okay. Then first row 1 and row 2 will be added using a 4-bit parallel binary adder. Then sum of this will be added to row 3, another 4-bit parallel binary adder. Then this and the last row will be added using another 4-bit parallel binary adder. And here we will be requiring 16 AND gates to generate the products. So, in the similar pattern, the circuit which is designed for 4x3 multiplier, we will be requiring another set of 4 AND gates at the output here. Here we will be requiring 4 more AND gates which will be computing the 4th row, and then this 4th row will be added to this 4-bit parallel binary adder sum using another 4-bit parallel binary adder. That means 3 4-bit parallel binary adders will be required and 16 AND gates. So, if you want to design 4x4 multiplier, so 16 AND gates and 3 4-bit parallel binary adders are required to realize a 4x4 multiplier. So, this I am leaving as an assignment. So, this is all about today's lecture. Thank you very much.